Okay, welcome back. And I hope that you went and looked up the intermediate value theorem from Calculus 1 and refreshed your memory on it. So here I have a statement of the theorem, just so that we all are on the same page. First of all, your function needs to be continuous on a closed interval. N, remember, is a y value, and it's between these two y values, f of a and f of b. And if you satisfy those two conditions, then the result we get is that there's at least one real number c in this interval. C is an x value, satisfying f of c equals n. So we're going to use this theorem to tackle this next proposition. Okay, so we're asked to prove that this equation has a unique solution. That means only one solution. And we are talking about real numbers. Just make sure that's obvious. So this is the plan. First, we're going to define a function so that we can use the intermediate value theorem. So we will have this function, and we'll need to do some scratch work because we've got to find this interval AB, because what are we looking for? We're looking for a zero. So when you're looking for a zero, the n in the intermediate value theorem is 0. And so we need to have n between f of a and f of b. And what you do is you look, we want one of these to be positive and one of these to be negative. And then 0 will be in between f of a and f of b. So we just start looking like, what is f of 0? That's -1, and that's less than 0. So that might be worth using. And what is f of 1? That's 1 plus 1 minus 1. Well, that equals 1, which is greater than 0. So we found our interval will be 0 and 1. Okay, so and then we'll write up the proof using the immediate value theorem. So what we have is that there's going to be some c that equals 0 in our interval. And what does f of c look like? It looks like this. So if we have that, we have a solution to this equation, which is what we were asked to do. Find a solution for this equation. Then we have to tackle this uniqueness question. Is it the only 0 of this function, or does this function turn around and come back down at some point? So our function between 0 and 1 somewhere crosses the x-axis. Now, if we can show that the function is strictly increasing, that means it's always going up, and it never turns around to come back down, and there would be another 0 if that happened. It also never does this on the other side. So for uniqueness, we need to show that this function is strictly increasing. And for that, if we can show that f prime of x is greater than 0 from negative infinity to infinity, we will have uniqueness. So let's see how we would start this. And this is a existence proof. and it is non-constructive because we're not going to say what it is, we're just going to show that it's there. So, in order to use the intermediate value theorem, we have to satisfy the hypotheses, which I will underline here in red. We need to be continuous on the closed interval, and our zero has to be between f of a and f of b. So what kind of function is this? It's a polynomial. So continuity is easy to establish. Polynomials are continuous functions. In particular, f is continuous on the interval that we just came up with, 0, 1. So note that f of 0 is less than 0 and f of 1 is greater than 0. So we have our number n equals 0 between f of a and f of b. F of 0 was negative 1 and f of 1 was 1. So, hence, by the intermediate value theorem, which I'm going to be lazy and abbreviate, there is some number c. Where is c? It's in this interval 0, 1, satisfying f of c equals 0. In other words, c to the fifth plus c minus 1 equals 0, which is equivalent to c to the fifth plus c equals 1. Thus, we have a solution. Now we have to talk about uniqueness. We're going to look at the derivative. What does it look like? 5x to the fourth, I believe. I should actually look at my function over here. 5x to the fourth plus 1. Now, is that obvious to you that this is always greater than 0? Well, it's an even degree polynomial, so it sort of has this kind of shape, and it doesn't cross the x-axis because it was lifted up 1 unit, vertical shift up. So this is always greater than 0. What does that mean? F is a strictly increasing function. And therefore, the solution is unique. The end. So, a lot going on there, but this is something that you can't forget. You've got to remember the intermediate value theorem and how to use it to find a 0 of a function. And you need to remember what it means for a derivative to be positive everywhere. That means your original function is strictly increasing. And so you might be wondering, why do we care about uniqueness? Well, from my own experience, I can give you an example. In estimating an unknown parameter, we're often looking for a maximum of some function. And we're using this maximum to estimate an unknown parameter, call it theta hat. And you want this maximum to be unique, because if you're trying to estimate an unknown parameter, you don't want to have two different numbers. You just want one maximum to represent this. So looking for a maximum, you take the derivative and you set it equal to 0. You find the maximum, and then you have to look at the second derivative to tell what's going on with the first derivative. It's like one layer down. But in any case, you have to establish that it's unique by showing that the derivative, not the original function, but in this case it's the derivative, is either strictly increasing or strictly decreasing. You want to know that you just have one maximum value. And of course, this is just extra, but sometimes it's hard to know why we care about things, and that's just an example I can give you. All right, so try the homework. I think you will have a quiz that's probably just one or two questions. One will be like this, though. So make sure you understand how this worked, and let me know if you have any questions.